Hello, and thank you for coming to SIG School Scholars. Today we'll be beginning a lecture series on kinematics. So, kinematics is one of the two branches of mechanics, which is in and of itself a branch of physics, one of the many branches of physics. Mechanics is the study of how and why objects move. And it's broken up into dynamics and kinematics, which so dynamics is going to be why they move. Kinematics will be how they move. So we're going to jump right in to kinematics. Okay, so before we can truly begin, we must discuss the difference between a vector and scalar, and also define some terms whose distinctions are somewhat ambiguous in common parlance. So, vectors. So a vector is a geometrical object that possesses both magnitude and direction, which is very important. A scalar I have to settle at 76. A scalar possesses only magnitude. No direction. Okay, now the first thing we're going to look at will be first set of terms we're going to look at. Going to be distance and displacement. And we're going to define the distinction between the two of them. And as we go through these terms, we'll state which ones are vectors and which ones are scalars. So, one way to think about this, a scalar is just going to be a number. Okay, a vector is going to be a number with a direction. And when we draw a vector, in this case, let's draw it from the origin. It's going to have some length, its magnitude. And that magnitude, let's call this vector V, will be defined as the square roots of the x component, square roots of the squares of the x component and the y component. Now this makes sense. Just think about the Pythagorean theorem. This is Vx and this is Vy. And to get V, we would do V squared equals Vx squared plus Vy squared. So V will equal the square root of Vx squared plus Vy squared. That's the magnitude of V. So this isn't necessarily that important right now, because we'll be talking about vectors, their addition, subtraction, everything to do with vectors in a later video. But this is a vector. This is what it looks like. This is how I usually draw them. It's like a directed line segment with some, and we define the direction as the angle between it and the x-axis. Okay, so let's, like I said, the first pair we're going to look at, first pair of related terms will be distance and displacement. So, distance is defined as how far an object traveled. The total, well, I don't want to say distance, but it's how far an object traveled. While displacement is going to be the change in position of the object. Let's use a couple different colors here. So, first, let's draw a coordinate plane. This is going to be north, south, east, and west. And this is how we're going to, let's go ahead and say that this object is going to travel 30 meters north, then 20 meters east, then 50 meters south, and then 20 meters west. So we want to find the distance this object traveled. The distance it traveled. Let's go ahead and use a different color here. Let's go with blue. So, distance it traveled will be that 30 meters north plus the 20 meters east plus the 50 meters south plus the 20 meters west. So we add them. 30 plus 20 is 50. 50 plus 50 is 100. 100 plus 20 is 120 meters. The total distance the object traveled will be 120 meters. So, now, what was the object's displacement? Okay, well, let's use green for this one. Very bright green. Displacement will be equal delta x, or a change in position, and this is going to equal final position minus initial position. Well, its initial position is the origin, x1. Its final position, x2, is well where it stops moving. Now this x1 at the origin is the point 0, 0. Now this x2 is going to be 0. Let's see, this was at 30, then went down by 50. That's negative 20. And these 20s cancel out, because they're in opposite directions. So what we have is then the displacement is negative 20 meters north or positive 20 meters south. So, displacement from the starting point is then, of course, a vector. As you can see, we had to assign a direction to it. And as you can see, this would be the displacement vector. So let's go back to the black. There. Vector. First vector is displacement. Our first scalar is distance. So that's going to be the difference between distance and displacement. Now, the next pair of terms we're going to cover will be velocity and speed. So, there we go. So, velocity versus speed. So, the difference between the two is that velocity is a vector and speed is a scalar. So, the magnitude of the velocity, 40 kilometers per hour west, because this just means that the velocity of the, let's say, for example, a car, is 40 kilometers per hour in the direction west. The magnitude of this velocity is going to correspond to the length of this vector, and the magnitude will equal the speed of the object. So speed is simply the magnitude of velocity. And therefore it's a scalar. So when we calculate speed, the difference between when we calculate speed and when we calculate velocity is that speed is going to be distance over time, whereas velocity is displacement over time. And our velocity is going to be our displacement. Because it's displacement over time, we can write it like this. So v will equal delta x over delta t, or x2 minus x1 over t2 minus t1. And this velocity is really just an average over an interval of time. So I mean, think about it this way. If we say a car traveled, and this is how we would calculate velocity. Let's go ahead and erase this right here. We say a car's displacement was how should we phrase this? How do we have a bowling? Well, that's probably not good enough. Oh, yeah, let's say a car. You have a car. Someone's driving a car, and they go on a trip, some trip. And they're like traveling for 4 hours, let's say. And they travel a total of what? What should we say? 500,000 meters? in 4 hours. Or that seems like, okay, that's too much for, probably too much. So I mean, let's say 10 hours. Let's go 10 hours, yeah. 500,000 meters is 500 kilometers. Well, let's go ahead and convert that to miles, see how long it is, see if that trip makes some sense, and also get some practice with unit conversion. Well, 1 kilometer is 1,000 meters. We can go from meters to centimeters, right? 1 meter is 100 centimeters. And then we can go from centimeters to inches, then from inches to feet, and feet to miles. 2.54 centimeters, 1 inch. See, how much space do we have left? Probably not enough. Okay, 12 inches, 1 foot, and then it looks like just enough space. Oh wait, I made a mistake. Okay, 1 mile, 5,280 feet. Okay, now see how they cancel? Feet, feet, inches, inches, centimeters, centimeters, meters, meters, and kilometers, kilometers, and we have miles. So, let me get my calculator. So, 500 times 1,000 is, of course, 500,000. That's what we started with. So we take that 500,000, multiply by 100 to get the number of centimeters, divide by 2.54 to get the number of inches, then divide by 12 to get the number of feet, then divide by 5,280 to get the number of miles, and we have a trip of 3 significant figures, 310.6855961119, which will be 311 with 3 significant figures, miles. Okay, well that sounds like a reasonable trip, sort of. Okay, now we have a 311 mile trip, and since we are using SI units, the metric system will use 500,000 meters. So we have 500,000 meters in 10 hours. So what we're getting here is actually an average velocity. So we can't expect that the driver is going to be traveling at a constant velocity the whole time. But this is basically what the traveler's velocity would be. Let's say we have 2 or 3 significant figures in each number. We have 10.0 hours, which we're going to have to convert to seconds, because that's the SI unit for time. And this is going to be 5.00 for 3 significant figures, times 10 to the 1, 2, 3, 4, 5 meters. So, 10 hours is, of course, multiplied by 60 to get minutes, and by 60 again to get seconds. There are 3,600 seconds in 1 hour. So what we have here is 3.60 times 10 to the, what was it, 4th seconds for 3 significant figures. 3.60 times 10 to the 4th seconds divided by 5.00 times 10 to the 5th meters. We're going to get, our answer will be in meters per second. So 500,000 divided by 36,000. Okay, well, their average velocity with 3 significant figures is going to be 13.9 meters per second. So, Again, this is an average. The person did not travel at a constant 13.9 meters a second. They had probably stopped, went to a gas station. I don't know what they did. Whatever. They slowed down. They stopped at stoplights, maybe. I don't know. But it's just going to be an average for that interval. If we and so that means that there's going to be changing velocity, and that's the next thing we're going to talk about. A change in velocity with respect to time is called acceleration. It's going to be our next term. Acceleration is going to be change in velocity over a change in time. Now this answer is accurate as long as the person did not accelerate, which is like impossible. Of course they accelerated. So we have v2 minus v1 over x2 minus x1, and our units are going to be meters per second squared, and basically means that the object increases velocity by x meters per second every second. And of course, we assume that our velocity, okay, and of course this is going to be an average as well, because over if the object is accelerating, we'd have to, if this is not an average and it is accurate, then like this, we're going to have to assume that their velocity did not change. Their acceleration was constant. However, most of the times when we do problems, our acceleration is going to be constant. So we're not going to have an average. We're just going to have acceleration equal to delta v over delta t. And we'll be able to assume a lot of times that there's, well, a lot of our problems will have no acceleration as well. So we'll have this. And then there are equations for kinematics that we're going to derive in our next video that take into account constant acceleration or non-constant acceleration. They'll take into account constant acceleration. So a changing velocity. So we won't have an average velocity. We'll have a what's called an instantaneous velocity. So we're going to add acceleration to our vectors, because it is in fact a vector. We can have a positive or negative acceleration. Usually we term, in common parlance, we term a negative acceleration a deceleration. However, since there's no reason why an acceleration can't be negative, we don't say deceleration in physics, usually. Thank you for watching the video. If you want us to make a video on a specific topic, just leave a comment either in the comment section below or on our website at sigschooltutors.wordpress.com, and we'll try to fulfill your request as soon as possible. Thanks.